Hi. So we're going to discuss design considerations for fire resistance in some common concrete structural elements. The purpose of this presentation is to provide you information on just that, and also to bring to light the importance of determining the fire resistance requirements based on a building code. And this is basically done prior to the structural design, and you'll see that once we get into it. Among the many unique virtues of cast-in-place reinforced concrete buildings, a couple are, one, for example, structural integrity, which is the ability of a structure through strength, redundancy, ductility, and detailing of reinforcement to redistribute stresses and maintain overall stability if localized damage or significant overstress occurs. Structural integrity in a building provides alternate load paths in the event of damage to major supporting member or an abnormal loading event. The ACI 318 building code includes requirements for structural integrity. The other is fire resistance, which is the property of a material or assembly to withstand fire or provide protection from it. As applied to elements of buildings, it is characterized by the ability to confine a fire when exposed to fire, to continue to perform a given structural function. Reinforced concrete is inherently fire resistant. Cast-in-place reinforced concrete buildings have a good track record from a fire resistance standpoint. Fires have shown their ability to do great harm to life and property, whether through arson, by accident, or by nature. Even without a single major event in a given year, fires account for a significant personal and economic drain. In 2013, according to the National Fire Protection Association, over 1.2 million fires occurred, resulting in more than 3,200 civilian deaths and over 15,000 civilian injuries and over $11 billion in direct property loss. Of these 1.2 million fires, about 500,000 were structure fires causing 2,800 civilian deaths and over 14,000 civilian injuries and $9.5 billion in property loss. So it's a big margin. A big margin is held by structure fires. Since fires are a major hazard, as related by history and the preceding grim statistics, the fire resistance of buildings is important in the protection of life and property against the hazards of fires. To mitigate a fire hazard, building codes regulate various aspects of building construction, including requirements for non-combustible materials and fire-resistant classifications depending on building use, occupancy, size, and location. Building codes throughout the country regulate the fire resistance of the various elements and assemblies comprising a building structure. These elements include structural frames, which include columns and beams. They also include floor and roof systems and load-bearing walls. Now, all of these elements must be able to withstand the stresses and strains that are imposed by a fully developed fire. At the same time, of course, they must sustain their own dead loads and superimposed loads without collapsing. Fire resistance ratings required of various elements by the building codes are basically a measure of the endurance needed to safeguard the structural stability of the building during the course of a fire, and also to prevent the spread of the fire to other parts of the building. Now, in the design of structures, building code provisions for fire resistance are sometimes overlooked, and this may lead to costly mistakes. It's not uncommon, for instance, to find that a concrete slab in a waffle slab floor system may only require 3 to 4.5 inch thickness to satisfy an ACI 318 strength requirement. However, if the building code specifies a 2-hour fire resistance rating for that particular floor system, the slab thickness may need to be increased to 3.5 to 5 inches. And this all depends on the type of aggregate used in the concrete. Now, under such circumstances and from an economical standpoint, the fire resistive requirements may indicate another system of construction to be more appropriate. For example, a pan joist or a flat slab plate floor system. Basically, what it is certain structural members possessing the fire resistant prescribed in building codes may differ significantly in their dimensional requirements from those predicated in the ACI 318. Now, most of the state and municipal building codes are modeled primarily after these two modeling building codes, one of which is the International Building Code. The version I'll be referring to will be the 2015, and then the NFPA 5000 Building Construction and Safety Code, which is the 2015 version. For simplicity reasons, I'm going to try to just reference the International Building Code, and you guys can take a look on your own, the NFPA version. Now let's go over some common terms you're going to hear throughout this presentation. First one, fire resistance rating. The IBC defines this as a period of time, usually expressed in hours, as a period of time a building element, component, or assembly maintains the ability to confine a fire and also continues to perform a given structural function. A non-combustible material, a material that under the conditions anticipated would not ignite or burn when subjected to fire or heat. Restrained is basically any condition in which the expansion at the supports of a load-carrying member resulting from the effects of a fire is restrained by forces external to the member. Usually this in terms of reinforced concrete members, this is helpful because since the elements expand, they compress the member, giving it a little more strength. Unrestrained is a condition in which the load-carrying member is free to expand and rotate at the supports resulting from the effects of a fire. In this section, we're going to go over the testing method used to establish a fire resistance rating of an assembly. Now, the test used to determine the fire rating of certain assemblies is the ASTM E119, which is the standard test methods for fire tests of building construction and materials. In this test, assemblies are subjected to a fire that follows a standard time temperature curve. The fire resistance rating of an assembly is determined by the duration of the test until one of the following set endpoints is reached, which is on the next slide. For the fire test, there are three endpoints that are looked out for when performing the test. One of them is flame passage. That's basically they have cotton waste on the opposite side of the assembly from the fire, and as a result from flames passing through or hot gases passing through, the cotton waste ignites, and that triggers the endpoint. Another endpoint is heat transmission. The temperature of the unexposed surface of the assembly rises to an average of 250 degrees Fahrenheit or a maximum of 325 degrees Fahrenheit at any one point. So total average of the whole area, 250 degrees, and then at any point the highest can be 325 degrees. Another endpoint is structural failure. The test specimen is unable to sustain the applied loading and collapses, which is an obvious endpoint. There's other additional fire resistance rating criteria which you can look up in the ASTM manual. Now, the results of many of these ASTM E119 standard fire tests on reinforced concrete members have been compiled and analyzed over many years. Along with the standard fire tests, there has been research and development of data on the strength of reinforcing steel and concrete at elevated temperatures, the temperature distribution within concrete, the verification and modification of theory, and the effects of restraining thermal expansion during heating. This extensive testing and research forms the basis for analytical methods of determining the fire ratings for reinforced concrete structural members. Determining fire ratings can be classified into two methods, the rational design and the empirical design. This is what we're going to get into in this next section. Now, determining fire ratings can be classified into rational design and empirical design. Rational design is accepted in Europe, it's in Australia, New Zealand, and in the United States it's accepted as an alternate. Rational design is a much more detailed design of the fire rating of a system. The other one is empirical design, that just works off of research and development from ASTM testings, and it just establishes minimum critical thicknesses of members, minimum cover for concrete members, and such. In rational design, the fire rating is the time required for the load capacity of a member to be reduced to equal that of the service loads. The rational design process for fire exposure has been included as an acceptable alternative to prescriptive methods in applicable codes in Europe, Australia, as mentioned in the previous slides. In the US, building codes have been kind of slow to adopt similar provisions. However, designers are permitted to present the results of a rational analysis for fire resistance rating as an alternate method of compliance. The rational design method, it's a three-step design, first of which being defining the exposure of the fire incident on the assembly. This can be from the ASTM E119 standard time and temperature curve, or another source, as long as it's agreed upon with the building official wherever it's codified. The heat transfer, calculating the heat transfer on the assembly, usually this may be determined by calculating using simplified methods such as tables or lump thermal capacity models, or even more advanced methods employing finite element programs in both 2- or 3-dimensional to establish the temperature profile within the assembly. The third step is the structural analysis, which uses established degraded material properties at elevated temperature. Basically, the structural analysis treats the fire as an imposed load and follows the same procedures that would be used under normal conditions, substituting modified values for concrete compressive strength, yield strength of reinforcing steel, and modulus of elasticity for both materials at elevated temperatures. Now let's go over empirical design. Empirical design uses the results of ASTM fire tests, such as data on the strength of heated reinforcing steel and concrete, and the temperature distribution in concrete. All this to establish critical member thickness, concrete cover, and so on. The application of empirical design is very simple. It's simpler than rational design, since the structural analysis is not required. For cast in place reinforced concrete, the term empirical design is just, it's not even accurate. A more accurate term would be an empirical approach, since there really is no design involved. Conforming to the requirements merely involves providing the required concrete cover for reinforcement and determining required thicknesses for a member, and so on. Now let's go over some design considerations for different building elements, first of which is wall assemblies. The fire ratings of reinforced concrete walls are nearly always governed by the heat transmission endpoint before the other two endpoints, one of which being allowing passage of flame or failing structurally. The table below lists the minimum reinforced concrete wall thicknesses for different types of aggregates to provide the required fire ratings. Now, in the next slide, you can take a look at what each of these aggregates are. As you can see, for, let's say, a 2-hour rating. Sand, lightweight, and lightweight aggregate types can give you a 2-hour rating at a lower minimum thickness than the other two. And you can go to the next slide and take a look at what each aggregate type it consists of. All right, so these are the structural concrete aggregates that you'll see again in the slide. So we're just going to go, you can read through all the definitions. I'm just going to quickly go through it. Silicious is aggregate is just consisting of silica. Carbonate is basically like limestone or dolomite. Sand, lightweight, is natural sand and also weighs between 105 and 120 PCF. Lightweight weighs even less, 85 to 115 PCS. Another structural element is floors and roofs. Similar to walls, the fire ratings of reinforced concrete floors and roofs are often governed by the heat transmission endpoint as well. Therefore, Table 1 is also applicable for reinforced concrete floors and roofs to determine minimum thickness. Table 2 listed here, it lists the required concrete cover based on the type of aggregate and restraint condition to provide the required fire rating. If you go back in the presentation, we've discussed restrained and unrestrained conditions. Here's an example of different types of scenarios where they would be classified as restrained or unrestrained. If you go down to the bottom, it says concrete framing. Most of it is restrained. We're dealing with restrained. If you go up to the wall bearing, there's some unrestrained and some restrained. So you can go through this, read, and get a better understanding of what we're talking about when we say restrained or unrestrained. Now for concrete floor joists, for standard joist construction, the equivalent thickness is based on the spacing of the ribs and thickness of the top slab. The equivalent thickness is determined, if you look at Figure 1, you'll see the graphic of what the spacing and the thickness represents. Basically, for spacing that's greater than 4 times the thickness, the equivalent thickness is T. For spacing less than 2 times the thickness, the equivalent spacing, the equivalent thickness is TE, which, if you look on the bottom, it explains what that is. And for spacing that's between 2 times the thickness and 4 times the thickness, the equivalent thickness is that equation right there. The S in all of these equations is the center spacing of ribs. T is the top slab thickness, and TE is the thickness of the joist section, calculated as the net cross-sectional area divided by the rib spacing, in which the maximum thickness used in the calculation doesn't exceed 2T. For beams, the fire rating of beams depend on concrete cover, the width of the cross-section, and the restraint condition. You can go through the table and take a look at different fire ratings and different beam widths allowed. Notice under unrestrained, 3 or 4 hour rating is not available for 5-inch beam width. For columns, the fire rating of a reinforced concrete column is influenced primarily by the column size and the aggregate type. The fire ratings of columns are related to minimum column size, as shown on Table 4, and minimum cover requirements, which are shown on the next slide. There are some exceptions, which you'll see in the notes, and also some exceptions, Table 5, which you'll see on the next slide. That pretty much wraps up our design considerations for reinforced concrete. Some benefits. Since reinforced concrete is composed of inherently fire-resistant, non-combustible material, there's no need for additional costly fireproofing. Cast-in-place reinforced concrete construction provides buildings with excellent fire endurance. In an actual fire, reinforced concrete floors and walls are likely to remain in place longer than the time reflected by the ASTM designation, since their fire resistance rating is determined by the heat transmission and not the structural failure. In most cases, just how long the walls and floors will continue to perform is unknown because the fire tests are often ended prior to the structural failure. Thank you for listening, and hope you enjoyed it.